Morning or afternoon, everyone. Today, we are diving into a critical and exciting area, edge-ready generative AI. Specifically, we'll be exploring how to engineer low-latency AI solutions designed for resource-constrained environments. As businesses increasingly look for real-time AI capabilities, right where the action happens, at the edge, understanding how to optimize these powerful generative models becomes essential. We'll look at systematic ways to maintain performance while cutting down on computational needs, power consumption, and latency. This opens up fascinating new possibilities for intelligent applications directly on edge devices. Just a little bit about myself. I'm Cyclian Reddy Pentaparthi, Principal Software Engineer at ST Engineering iDirect. My work focuses on enhancing global connectivity through advanced IP satellite network infrastructure. My experience in network engineering and software development gives me a practical perspective on challenges and opportunities of deploying complex systems like AI in diverse environments, including the edge. You can find more details or connect with me on LinkedIn. So, why is edge AI challenging? Let's look at edge computing frontier. Unlike the seemingly limitless resources in the cloud, edge devices operate under significant constraints. First, limited computational resources. Think processing power, memory, storage. Edge devices typically have much less than cloud servers. Second, connectivity challenges. Edge solutions often need to work reliably even with spotty, slow, or sometimes no internet connection. Third, energy constraints. Many edge devices run on batteries or have strict power budgets, limiting how complex our AI models can be. And finally, real time requirements. Many edge applications, like autonomous vehicles or industrial monitoring, demand immediate low latency responses, putting high performance demands on these constrained devices. Despite the challenges, the demand for edge AI is booming. Let's look at market trends. We are seeing strong expansion. The edge AI accelerator market, the specialized hardware, is growing incredibly fast, nearly 39% CAGR, projected to hit almost 7.7 billion by 2027. This signals huge demand for on-device AI. What's driving this? Key adoption drivers are primarily the need for low latency. Over 78% of organizations cite this as crucial for real-time responses. Then data privacy is another major factor. Almost 65% of organizations cite this as another major factor. Pushing processing locally instead of sending sensitive data to the cloud is important for them. And the industry is adapting. Model optimization techniques, which we'll discuss heavily today, are already used in 82% of deployments. This shows a clear focus on making complex AI run effectively on edge hardware. The edge AI market evolution. Let's look ahead. We are really at an inflection point. Currently, generative AI at the edge is still limited by those resource constraints that were mentioned. But over the next 12 months, we expect increasing adoption of optimized edge AI solutions. Within 8 to 24 months, the prediction is that most enterprises need real-time edge capabilities will be actively deploying them. Beyond 2025, edge AI is likely to become ubiquitous, supported by specialized hardware acceleration. This rapid evolution is driven by hardware advancements, better optimization techniques like quantization and pruning, and the growing need for privacy preserving local computation. The shift away from cloud dependency for real time tasks is well underway. Edge AI market trends. Just to reiterate, those key market drivers because they underscore the why behind the edge optimization. The market growth is significant. As mentioned, 39% of CAGR for accelerators and 7.6 billion market cap soon. The primary need for low latency for immediate responses and data privacy, both favoring local on-device processing. And crucially, the industry is already heavily invested in model optimizations, which is done in like almost 82% of deployments to overcome hardware limitations. This sets the stage for the techniques we are going to explore in the rest of the talk. Hardware acceleration solutions. Software optimization is key. Hardware plays a vital role. Specialized hardware acceleration solution dramatically boost performance and energy efficiency for the edge AI. We have neural processing units, NPUs, which are dedicated AI accelerators, now common in modern systems on chips. They offer 10 to 15 times the energy efficiency for a standard CPU for typical neural network tasks. Google offers HTPUs, purposely built edge accelerators, providing significant processing power, like up to 4 tera operations in small, low power, around 2 watts package. That's impressive. Then mobile GPUs are also increasingly optimized for AI, leveraging their parallel processing power. And FPGA accelerators offer reconfigurable hardware adapted for specific AI models and often very power efficient in production. These accelerators are designed specifically for the math intensive operations common in AI, like matrix multiplications. GPU's overview. This table gives a snapshot of the diverse landscape of GPUs and accelerators. Don't worry about memorizing the details, but notice how the key players like NVIDIA's Jetson series, like Nano, Orion NX, AGX Orion, RTX ADA, AMD's Ryzen AI, Intel's Core Ultra NPUs and ARC GPUs, Google's Coral, the HTPUs, Qualcomm Snapdragon's NPUs, and specialists like Edge Cortex. The important takeaway here is the variation in AI performance, memory capacity and bandwidth, power consumption, and form factor. Choosing the right hardware depends heavily on specific application needs regarding performance, power budget, and physical size. This plays a critical role in the process of developing these models. Now, let's look at the inference performance, specifically for large language models, which are notoriously resource intensive. Again, this table is illustrative based on available data, which can be fragmented. Key things to note: high-end desktop GPUs like RTX 4090 or 3090 achieve very high throughput tokens per second using optimized frameworks like NVIDIA's TensorRT LLM, significantly outperforming less optimized methods like llama.cpp on the same hardware. For edge-specific hardware like NVIDIA Jetson's Orion series, AMD Ryzen AI, and Intel Core Ultra, running models like Llama or Mistral 7B, often using quantization like integer 4, is becoming feasible, especially with dedicated frameworks like TensorRT LLM, ONNX runtime with VTIF AI, IPEX LLM, OpenVINO. However, specific standardized benchmarking numbers for throughput and latency on these edge platforms is still emerging and depend heavily on software maturity and optimization levels. That's why we see needed data in specific rows and columns. The power consumption is drastically lower for edge devices compared to desktop GPUs, highlighting the efficiency gains but also performance trade-offs. Beyond physical hardware, hardware is only part of equation. Software, specifically AI frameworks and optimization engines, is crucial for actually running models efficiently on the hardware. Key AI frameworks like TensorFlow Lite and PyTorch Mobile are designed for edge deployment. NVIDIA's TensorRT and its LLM variant are highly optimized for their GPUs. Inference optimization engines like ONNX Runtime and Intel's OpenVINO focus on optimizing models for efficient execution across various hardware. Vendors also provide specific software stacks like NVIDIA Jetpack, AMD Ryzen AI software, Intel's One API tools, and Qualcomm's AI stack, which bundles drivers, libraries, and tools for their respective hardware. Choosing the right framework involves trade-offs. As this chart illustrates, TensorFlow Lite generally offers excellent hardware support through its delegation system, allowing it to leverage NPUs and GPUs effectively. ONNX runtime often provide slightly better raw execution speed and great cross-platform portability. PyTorch Mobile is often praised for its developer experience and simpler deployment, making it good for rapid prototyping. TVM, Apache TVM, can achieve the best performance through deep compiler optimizations, but also comes with significantly higher deployment complexity. So the choice depends on your priorities. Broad hardware support, it's TF Lite. Raw speed and portability, ONNX runtime is the one to explore. Ease of use, PyTorch Mobile. Or maximum performance at the cost of complexity, TVM. LLM automation techniques. Now let's get to the core software automation techniques, especially critical for large models like LLMs on the edge. The most crucial technique and the one we'll spend significant time on is quantization, reducing the precision of numbers used in the model. Next is network pruning, removing redundant pairs of the neural network. Then there is knowledge distillation, training a smaller student model to mimic a larger teacher model. Other methods include low rank approximation or factorization and various memory optimizations. Today, we'll focus primarily on top three: quantization, pruning, and knowledge distillation. Start with quantization. The fundamental idea is to use fewer bits to represent the model's weight and activations, reducing size and often speeding up computation. There are several approaches. Post-training quantization, PTQ, is the simplest. We train our model normally, usually in 32-bit floating point numbers, and then convert it into lower precision, like 8-bit integer, represented as int 8 or even int 4 afterwards. It's easier, but might have a moderate accuracy cost. Next is quantization-aware training. Incorporates the effects of quantization during the training process. The model learns to be robust to lower precision. It's more complex, but usually preserves better accuracy. Then dynamic range quantization adjusts how quantization is applied based on the actual values encountered during inference, offering a balance between accuracy and performance, especially good at varying inputs. Precision-aware quantization. This visual helps illustrate the concept. Standard training uses FP32. PTQ simply converts this FP32 weights int 8 or int 4 after training. QAT simulates this conversion during training, allowing the model to adapt. An advanced technique is mixed precision deployment. Here, you don't have to quantize the entire model uniformly. You can analyze which layers are most sensitive to precision loss and keep them at higher precision, like FP32 or FP16, while aggressively quantizing less sensitive layers to integer 8 or integer 4. This offers a fine-grained trade-off. Quantization is powerful. Moving from floating point 32 to integer 8 can make models 4 times smaller and inference 3 to 4 times faster, especially on hardware with integer 8 support. Inference is a stage where model makes prediction on not seen data. Let's talk about quantization technique, PTQ. Diving deeper into it, what is it? Converting pre-trained FP32 model after training is complete. Pros: it's simpler and faster to implement because we don't need to modify the training pipeline. No retraining is needed. Cons: it generally leads to higher accuracy loss compared to QAT, especially when going to a very low precision like integer 4. It often requires calibration dataset, a small representative dataset used to determine the best way to map the floating point 32 ranges to integer 8 or integer 4 ranges. For many models, PTQ to int 8 results in less than 2% accuracy degradation, which is often acceptable because edge, the use cases are like not very generic like this, very domain specific actually. Why is quantization, particularly to integer 8, so beneficial for hardware? Let's look at the specs for NVIDIA A10 GPU, often found in servers but illustrating a common principle in accelerators. Notice the performance figure. For standard floating point 32 math, it delivers 31.2 teraflops. But look at the integer 8 performance using its tensor cores. 250 tera operations per second, potentially up to 500 tops with sparsity features. This massive increase in throughput for integer 8 operations compared to floating point 32 is why quantization is so effective and so critical. Hardware accelerators often specifically designed to perform low precision integer math much faster and more power efficiently than a floating point math. Quantization technique. What is it? Simulating the effects of quantization during the model training process. It generally achieves better accuracy preservation compared to PTQ, especially at lower bit depths, because the model learns to compensate for the precision loss during training. What are the cons? It's more complex to implement as you need to modify the training code and pipeline. It requires access to the original training data and that massive infrastructure. Training time is longer. QAT often keep accuracy degradation below 1.5% for integer rate, potentially even better than PTQ. Dynamic range quantization. Adapting the quantization parameters like the scaling factor based on the range of activation values observed at runtime rather than using fixed parameters determined offline. What are the pros? Offers a good balance between the simplicity of PTQ and the accuracy of QAT. It adapts to characteristics of the input data being processed. It can also reduce memory bandwidth needs as activation ranges are determined on the fly. What are the cons? There can be a potential runtime overhead associated with calculating these ranges during inference process because this runs on the edge, although often minimal on supported hardware. Next quantization technique, mixed precision. Using different numerical precision levels for different layers within the same model. So what are the cons with this approach? Provides an excellent way to balance compression and accuracy. We can keep critical sensitive layers at higher precision, example floating point 16 or floating point 32, while quantizing other more robust layers aggressively into integer 8 or integer 4. It requires careful analysis to determine which layers are sensitive. It also needs framework and hardware support to handle computations involving multiple different data types within the same inference pass. Studies have shown potential for significant compression, example up to 70% with minimal accuracy loss, like less than 1% using mixed precision. Because when you convert some of the layers to integer rate, it offers more model compression also. Next major problem optimization technique is neural network pruning. The core idea is that many large neural networks are over-parameterized. They have redundant weights or neurons that don't contribute much to final output. Pruning aims to identify and remove these non-essential parts. The process generally involves identifying redundancy by analyzing weights or activation patterns, then removing these elements. This can be structured pruning, where entire filters or neurons are removed, often better for hardware speedups, or unstructured pruning, where individual weights are removed, leading to sparse networks. Techniques like iterative magnitude pruning gradually remove small weights while retraining the network to maintain accuracy. Sensitivity analysis is often helps to evaluate how removing certain parts impact overall performance. Effective pruning can reduce model size significantly, sometimes 50 to 90%, with very minimal impact on accuracy, creating leaner, faster networks. So here's an overview of the pruning process. Step 1, training initial network. We start by training a potentially over-parameterized network until it converges and performs. Step 2, identify and remove unimportant elements. This is crucial step where we apply the criteria like weight, magnitude, activation frequency, impact on loss to decide which parts are unimportant and remove them. This might involve setting weights to 0, unstructured, and removing entire structures like filters, which is a structured way. And then step 3, fine-tune prune network. After removing elements, the network's performance usually drops. So we retain the smaller prune network for a few cycles. This allows the remaining weights to adapt and often recovers most, if not all, of the lost accuracy. This cycle of prune and fine-tune can be repeated iteratively to reach a desired level of sparsity and size. Let's look at specific pruning types. Magnitude-based pruning. is perhaps the simplest and most common. It operates at the granularity of either individual weights, weight pruning, which is unstructured, or entire units, neurons, or filters, which is a structured pruning. For weight pruning, we simply remove weights with the lower absolute values closest to zero, assuming they contribute least. For structured pruning, we might remove entire filters based on the sum or average magnitude of their weights. And the result, unstructured pruning leads to sparse, irregular weight matrices. Structured pruning results in smaller but still dense matrices, which are often easier for standard hardware to accelerate. What are the pros? Simple concept, high compression potential, especially unstructured. Structured pruning often gives better inference speedups on standard hardware. What are the cons? Unstructured pruning often needs specialized hardware or libraries for speedups, while structured pruning is coarser and might impact accuracy more. Pruning technique, importance based. Beyond just magnitude, importance based pruning uses more sophisticated matrices to decide what to remove. What is the mechanism? Instead of just looking at the weight values, it might consider the effect on the loss function if the weight were removed, using techniques like Taylor expansion or optimal brain damage or other algorithms. They analyze neuron activation or analyze gradient information during training. Goal is to make a more informed, sophisticated selection of which elements are truly unimportant for the network function, potentially preserving accuracy better than simple magnitude pruning. Creative based pruning technique. What's the mechanism we use here? As we see in the process diagram, it involves repeating the cycles of prune, fine tune. We remove a small percentage of weights or neurons, retain briefly, then remove some more, retain, and so on. The goal is to reach the target sparsity or size gradually, rather than removing everything at once. This gradual approach generally leads to better accuracy prevention for a given level of sparsity compared to one-shot pruning. What are the trade-offs? It's most time-consuming due to multiple pruning and retraining steps. A fascinating related concept is lottery ticket hypothesis. It proposes that dense, randomly initiated networks contain sparse subnetworks called winning tickets that, if trained in isolation from the start using their original initial weights, can achieve performance comparable to full dense network. Magnitude pruning, especially iterative pruning, is effectively a method to find these winning tickets within the large network. What are the implications? This suggests that the inherent sparsity might be a fundamental property of trainable neural networks. We don't necessarily need the huge dense network, we just need to find the right sparse structure within it. This provides theoretical backing for why pruning can be so effective without catastrophic accuracy loss, which is important for the edge. Last technique, knowledge distillation for the edge. Imagine we have a large, complex, highly accurate teacher model. It performs great, but it's too slow or large for the edge. We also have a much smaller student model, which is lightweight enough for the edge deployment, but might not be as accurate on its own. Knowledge transfer is a distillation process, which works by training the student model not just on the ground truth labels, but also to mimic the output of teacher model. Specifically, the student learns from the teacher's soft targets, the full potential distribution across all classes that teacher predicts, even for incorrect classes. This encodes richer information about how the teacher model thinks and generalizes. This allows the small student model to benefit from the knowledge learned by the much larger teacher, often achieving significant better accuracy than if it were trained only on hard labels. So knowledge distillation based technique based on the type inferred. This is the most common type, focusing on matching the output layer of the student to the teacher. Using those soft labels that were mentioned, it captures the teacher's final prediction reasoning. Examples show a significant parameter reduction while retaining high quality, up to 91% of teacher. This goes deeper, trying to match the activations in the intermediate layers of the student and teacher. The goal is to encourage the student to develop similar internal feature representations as that of the teacher. We can also categorize distillation by how the training happens. This is the standard approach. First, train the teacher model completely, and then we use the frozen pre-trained teacher model to train the student. Then there is online distillation. Here, the teacher and student models are trained simultaneously. They learn together, potentially influencing each other, which can sometimes lead to better results than the sequential offline train approach. An interesting variant where a model distills knowledge from itself. Often deeper layers of network act as a teacher for shallower layers, acting as a student. This can improve the performance of the single model without needing a separate teacher. This is used when there is a very large gap between teacher and student size or model capabilities. Beyond optimizing existing large models, another crucial strategy is to use edge-optimized model architectures from the start. These are neural network designs created specifically for efficiency on resource-constrained devices. Example includes mobile nets, famous for using depth-wise separable convolutions, which drastically reduces computations like 8 to 9 times, compared to standard convolutions, great for vision tasks. Shuffle nets use channel shuffling and group convolutions, further optimizations for low power devices. And then SqueezeNet employs FIRE modules to reduce parameter counts while maintaining classification accuracy. And then the EfficientNet uses a compounding scaling method to intelligently balance network width, depth, and input resolution for excellent efficiency and accuracy trade-offs. Using these pre-built architectures is often more effective than simply shrinking a standard large architecture, as they incorporate efficiency principles directly into their design. Let's look at a practical example, an edge voice assistant. Using a combination of the techniques, likely neural network pruning and 8-bit quantization, a baseline model was optimized. The results? The optimized model achieved 98.2% wake word accuracy with a very low false activation rate under 0.5%. It managed 87.3 command recognition accuracy across different noisy environments. Crucially, the model size for the entire system, wake word plus command recognition, was reduced to just 76 MB, a 73% reduction from baseline. And the response latency was only 85 milliseconds end to end, well within the threshold for a real-time feed. Knowledge distillation from a larger teacher model likely helped maintain the higher accuracy despite the significant size reduction. This demonstrates how these techniques deliver tangible real-world benchmark performance benefits on the edge. Takeaway and implementation details. So, what are the key takeaways? First, establish performance targets. Be clear about the latency, accuracy, power, size budgets before the start of optimization. Secondly, apply the integrated optimization. Don't just rely on just one technique. Combine pruning, quantization, distillation, and potentially architectural choice for the best results. Their effects are often multiplicative. Third, test on target hardware. Emulators aren't enough. Benchmark and profile directly on the edge devices we deploy onto to find the real bottlenecks. Fourth, iterate with real-world data. Edge environments can be unpredictable. Continuously collect data and refine the models after their deployment. Successfully deploying the generative AI at the edge needs this systematic iterative approach, considering the whole pipeline. A quick word on benchmarking. It's absolutely essential to know this. We need to define metrics clearly: latency, throughput, accuracy, power. Create a standardized test environment simulating real deployment conditions. Measure performance comprehensively across different hardware and workloads. And critically, use benchmark results to further guide optimization iterations. Systematic benchmarking validates the optimization efforts and ensure the solutions perform reliably and consistently in the real world. This is important because if you have seen, there are multiple choices to make. So what choices need to be made and which techniques, which combination of techniques needs to be done, can be only determined if we have a standard benchmarking. So we can run this iteratively and find if the combination actually reaches our benchmarks. Then finally, the implementation roadmap. What are the practical steps if we have to do this? First, audit model requirements. Understand the constraints and performance needs. And then prototype optimization pipelines. Test techniques individually first to see their impact and implement combined approach. Integrate the chosen techniques, pruning, quantization, distillation carefully, and deploy and monitor the observability aspect. Realize the optimized model, but include telemetry to gather real world data, performance data for continuous improvement. Start with audit, build systematically, validate thoroughly, and monitor continuously. That concludes our look into engineering low latency generative AI for the edge. By applying techniques like quantization, pruning, knowledge distillation, and choosing appropriate architectures and hardware, we can overcome resource constraints and unlock powerful AI capabilities directly on the edge. Thank you for your time and attention, and have a good day.